Thank you, and shame that I can't hear anyone, but thank you very much all for joining today. I'm going to be talking through a case study, predominantly on a case study relating to the adoption of geopolymer as the solution to maintain a rail project. The last time I presented on this case study, I was asked what else can geopolymer be used for, so I've added in a few project snapshots afterwards just to take you through some of the alternative uses of geopolymer. So this is the content of the presentation. It's an introduction to GeoBear and geopolymer, and then a focus on the engineering with geopolymer, and then the principal case study followed by 4 snapshots associated with different areas of solutions that we offer at GeoBear, and then some of the key contacts from the rail industry that we have here at GeoBear. So an introduction to GeoBear. So we're a global leader in the use of geopolymer for sustainable asset maintenance and remediation. The organisation was founded in the 1970s, became global in the 1980s, and it was rebranded from Eurotech to GeoBear in 2017. We deliver projects throughout the UK and are also present in the USA, Sweden, Finland, Poland, and China. We have a full in-house design team that I'm part of, providing designs to service our internal teams as well as external consultants and laboratories. And we've completed laboratories, and we have completed over 200,000 projects worldwide. So we work across all of the land-based built environment sectors. We offer numerous solutions, including ground improvement, stabilisation, relevelling, structural support, void filling, and water sealing. So ground improvement is where the strength of the soil or the load-bearing properties of the soil is improved. Stabilisation is where flexure or rocking of a slab is stopped, so that it no longer has that behaviour and it's a sound running surface, for example. Relevelling is applied on, for example, slab tracks or warehouse floors. Structural support is where a high stiffness element is introduced to transfer load to depth. Void filling is where voids are infilled, whether or not these are natural or man-made. And water sealing is where the water ingress rate of water through the soil or through a void is reduced. So today we're going to be focusing on the railways. We have 3 different types of vehicle within our fleet. Well, 2 vehicles and 1 rail container, allowing us to have access to the vast majority of sites. We work closely with contractors to make sure that we can access all sites. And in terms of our credentials, we hold BBA certification for our injection technology. We also have HAPAS accreditation for slab stabilisation, and we're ISO 9001 certified for quality management. We've worked with the industry, with specialists in the industry to prepare, for example, this specification document for specifying geopolymer for ground engineering applications, and we continue to work with the industry to improve our practices. And we have recognition for the successful implementation of geopolymer for various new and innovative purposes. And we have carbon champions in the business, and we are identified as a low equivalent carbon dioxide alternative. So an introduction then to geopolymer itself. So on the video on the right hand side here will play, and basically what that is showing is the process of expansion of the geopolymer once the 2 parts of the system are combined into a void. So it's a system that's formed from a resin and a hardener, and they're combined using the injection gun immediately prior to being injected through an injection tube. So everything comes to site in a single mobile workshop. The barrels of the resin hardener are in there, along with the pumps, the hoses, and the injection guns. And typically the workshop can be parked any distance, up up to 80 meters from the injection position, but we can extend this to approximately 120 meters. So that allows us to access many areas where access would otherwise be very challenging. And the process of injecting geopolymer is very low disruption. So the injection tube is inserted through typically 14 to 16 millimeter diameter holes, and the tubes themselves are pushed or vibrated to the treatment depth, depending on the specific treatment being carried out. So this is just the injection process again. So drill through any surface obstructions, usually 14 to 16 millimeters diameter. The injection tube, which is a steel 12 millimeter diameter tube, it's inserted to the treatment depth, and then the injection is carried out. If lift is required, we would monitor the lift. If lift is not required, then we monitor to make sure we don't lift. So we always monitor our injections to make sure we are aware of the impact that's being had there. So on to engineering with geopolymer. So the physical properties of geopolymer, so that there's I think at GeoBear we have access to 30 different options of geopolymer, but we typically use 10. So and typically it's 1 to 2 are used on a specific project. So in terms of expansion, geopolymer will expand in open air conditions between 3 and 40 times the liquid volume, and the expansive pressures can easily exceed 500 kPa for the most expansive geopolymers. The elastic modulus will vary from 2 MPa for our most expansive and lowest strength geopolymer to 120 MPa in open air conditions. Again, when it's confined within the ground, it can exceed this because the density is higher, and therefore it can reach up to 300 MPa in confined conditions. Also related to the modulus is the resistance to cyclic loading. When geopolymer is appropriately specified, it is fantastic in cyclic loading. You can see here on the left-hand side an example of a poorly specified material. You can see how it's tested, and as the cycles increase, the overall movement in millimeters is increasing, so that shows some plastic deformation. On the right hand side here, there is no plastic deformation. The material has been appropriately specified, and therefore this is the kind of design work that we put into these in specifying the design of the geopolymer. So strength, so the compressive strength can be up to 2 MPa for the working conditions. Ultimate is higher, but that's the kind of working strength. In the ground, it can exceed 7 MPa, and that's the compressive strength. For the working tensile strength, it's slightly less than this, so 1 MPa in open air conditions, but can exceed 6 MPa when confined in the ground. For our void filling non-structural geopolymers, the strength is much lower than this, but when strength is needed, then that's taken into account there. And the material is lightweight, so it ranges from, so the geopolymers that GeoBear offer range in weight, once they're set, to between 6 and 60 times lighter than concrete. So a little on the nature of geopolymer. So we've had a number of leachate tests carried out, one by ESI, who now Stantec, and Vertase LI. The ESI trial has identified that geopolymer injections are not a groundwater activity, and the Vertase leachate trial stated that there was no evidence of significant deterioration of water quality. And a desk study by Plixant has determined that GeoBear geopolymers have no or little environmental impact on soil and groundwater. The geopolymer solution is a water-free solution, so there's no additional water that needs to be brought to site to complete the treatment works. The water that's required for the reaction is contained within the barrels. So geopolymer is durable and resistant. It's It has excellent chemical resistance, and this has been proven via immersion testing. We've tested it for petrol, diesel, and acids at 10% concentration. Acids that are purely acids, it's not so durable in, but it's not a normal environmental. It's not a normal kind of situation to encounter. And then an extensive data review by Dixon has concluded that the longevity of geopolymer is in excess of 120 years in normal ground conditions. And the material hardens rapidly. So within less than a minute, the surface of geopolymer is typically hot. And then within a number of hours, geopolymer is fully hardened, allowing for the asset to start being used rapidly after treatment. So geopolymer develops differently whether or not you're working in a coarse-grained or a fine-grained soil. So in granular soils, the material fills the pore space between the clasts, creating essentially a matrix and binding the soil into these kind of bulbs. And in clay soils, the geopolymer expands and essentially hydrofractures the clays, create layers, high strength layers within the clay, providing confinement and strengthening. So I've just seen this comment, but I'll get to those at the end. The case study. So onto the case study. So the case study is the stabilization of a level crossing. So the case study is located in northeast of UK, and it was suffering from a sudden onset of settlement. It was the reason for the movement was due to washout and potentially poor drainage following flooding, but the level crossing itself had been renewed just a year prior. So level crossing was founded on a concrete raft that had deviated by as much as 60 millimeters, and the railway had deviated by as much as 25 millimeters. And then, of course, the settlement tolerances had been exceeded, and there was a rough ride for the rail and the road. So because the reinforced concrete raft itself remained in a good condition, stabilizing the ground underneath and re-leveling was deemed a viable option. The alternative was complete renewal of the raft and the level crossing, involving demolition of the raft, excavating affected soils and reconstruction, which for this purpose we've given a renewal design life of 60 years. It's an important assumption made in this study. The geopolymer solution was elected. It was deemed to be a more sustainable alternative to renewal. Purely, we have evidenced that we can provide dependable performance to support the economy from an economic standpoint. We have much lower disruption with the works being carried out rapidly, and what we'll go on to speak about further in this presentation is the lower carbon footprint associated with our works. And we were therefore contracted to reinstate the subbase and to re-level the raft slab. So the works were undertaken using geopolymer injected immediately into the subbase, so of the concrete raft slab there. We drilled a grid of holes on a 1.5 by 1.5 meter spacing, and through which we installed the 12mm steel tubes. And the works to reinstate the subbase and to re-level the level crossing was completed in 2 12-hour shifts. So the post-treatment monitoring, as shown here on the right-hand side, indicated that there was a 1mm settlement within the year following our treatment. So you can see on the left-hand side of this blue line that between January and April there'd been a significant deterioration of 25 millimeters. We then re-leveled the slab, and over a year the monitoring showed there was a 1mm of movement. So what we tried to do for the purpose of this carbon case study is to match the performance. So we've said if after 20 years the rate of deterioration remained at 1 millimeter per year, although we wouldn't expect that necessarily, then after every 20 years we'd need another geopolymer treatment, just to try and give us a baseline from which to marry up this carbon study. So we commissioned the carbon study with Carbon Footprint Limited, and the intention was to compare the geopolymer treatments, or 3 geopolymer treatments, to 1 renewal of the level crossing. It was undertaken on a cradle to gate basis over an assumed 60-year lifespan for level crossing under normal conditions, and the assessment considered various factors, including the material production, material transport using typical fuel usages, and on-site fuel use and travel using machine specifications. As I said previously, the comparisons made on based on a service life of 20 years for each geopolymer treatment and a 60-year design life for a renewal, and it's a key assumption, but we had to base the study on something, so that's what we went for. I think in both cases the performance of the geopolymer would be better than that, and the design life of the level crossing would ideally be longer than 60 years as well. So this is a comparison of the materials for each solution. So we have on the right hand side here the level crossing renewal, so 64 tons of reinforced concrete for the slab, 26 tons of railway sleepers, 61 tons of steel reinforcement, 9 tons of steel track, 65 tons of ballast, and 150 tons of sub-base to the raft. This is on the basis that nothing could be recycled at the moment, but at the end of this case study discussion, I'll show you what the reduction is if all those things asterisked were fully recycled. And the materials would be travelling between 175 and 450 kilometres within the UK, with the concrete sleepers imported from the Netherlands. For the 3 treatments using geopolymer, the total would be 1.9 tonnes of geopolymer and 110 kilograms of steel injection tubes used, with the geopolymer imported from the Netherlands and steel tubes coming from within 50 kilometres of the site. So for the geopolymer treatments, this is a breakdown of the equivalent carbon dioxide in kilograms. So the raw material, 6,000 equivalent carbon dioxide kilograms of CO2e, and then the remaining items, they're adding up to just under 10,000 for all 3 treatments. For a renewal, you have the raw materials coming in at 186,000, and then the additional elements there of raw material transport, on-site fuel, and on-site transport, adding up to just under 200,000 kilograms of equivalent carbon dioxide. So, in essence, for that case study, the case study is based on a 60-year life cycle. 2 key assumptions have been made in relation to the performance of geopolymer and the design life of a renewed raft slab for the level crossing. You can see from the comparison that the geopolymer treatment has a equivalent carbon dioxide the equivalent carbon dioxide content effectively of the geopolymer treatments is 95% less than the renewal. This is a substantial difference. Going back to those elements that I put asterisks on the previous slide, if we were to say all of those items were recycled, there's still an 88% reduction in terms of carbon between a traditional replacement and the geopolymer injections, and 3 geopolymer injections. So in summary, geopolymer injections delivered a significant equivalent carbon dioxide reduction compared to the traditional alternative in this case. Okay, so that's the main comparison study that we've undertaken. and now go on to some additional project spotlights just to cover some of the other uses of geopolymer in maintenance. And one or two of them aren't strictly maintenance, but I'll come back to how they can be used in maintenance projects. So this first one is very similar to the case study in that we have a raft, two raft slabs separated by a drainage channel and it's associated with the Chorley Tunnel. The tunnels had settled by the tracks had settled up to 50 millimeters along lengths of between 5 and 10 meters. You can see here on the right hand side. Subsidence was due to washout of fines due to block drainage, and we were contracted to infill voids and re-level the rafts. And we haven't got the specific data for it, but based on the previous case study I presented, we've deemed this to be a low carbon alternative. We worked closely with Network Rail to plan the works. We undertook the drilling works in possessions in advance of the 17-hour-long possession that was used to re-level the slab tracks. So the works were undertaken in passes. So we lift on each pass we lifted by up to 5 to 10 millimeters, and we had 5 passes to re-level the slab track, and we re-leveled the slab track to within 7 millimeters of design level during that 17-hour possession, and the speed restrictions on the line were removed after 2 weeks of monitoring. Okay, the second one is on ground improvement. The second spotlight's on ground improvement. So the video is going to play down here, showing the before and after of the condition of the rail before and after our treatment. So this is a slab track that had severely deteriorated and done so rapidly, and it resulted in a rough ride and cracking of the slab. The issue was determined to be soft soils rather than washout, although there were drainage issues. And so we were contracted to improve the soils rather than, and no lift was needed. Again, no specific data on carbon, but given the previous case study, we've deemed this to be a low carbon alternative. In this case, injections were carried out to a depth of 1.5 meters below ground level, and you can see from the video and from this graph, which essentially the data that the video presented, the before movement during the passing of the vehicle was between 5.5 and 6.5 millimeters, and after treatment it was at most 2 millimeters. So that's a 70 to 80% improvement in performance. Water sealing. So again, a video will play on the right hand side here. I've sped this up 12 times, but it's essentially it's an excavation below the groundwater table. It's supported by sheet piles and props. The rate of water into the excavation was too fast. The contractor could not pump fast enough, and so we were contracted to seal and reduce ingress rate where the sheet piles were leaking, and they were leaking because the clutches had separated as they were driven in some places. So the alternative to us undertaking those works was to backfill the excavation and then undertake jet grouting or potentially welding, although there were concerns with water flows, water pressures and safety. So we were considered to be the most sustainable option to infill the flow paths. And so in that case, the leaks were progressively sealed and the water ingress was reduced to allow for the works to carry on so the contractor could use pumps and the concreting works could be carried out. Just further to the water sealing, on the right hand side here is a video. This again has been sped up. It's showing us working alongside tunnel boring machines to seal leaks as they arrive during the works. See there was a significant leak which has rapidly stopped in 2 locations. So the leak was occurring in this location here and underneath the machine here, and our injection tube is inserted in that location, and in both places the leaking stopped. And we've also used our geopolymer to line brick tunnels to improve to reduce the amount of water coming through brick tunnels. So the last slide is for void filling. The video down here is going to show geopolymer being injected into badger sets. So on this project, it's a railway embankment. There was 33 badger sets of between 1 metre and 5 metres in depth or length from surface, and there was badger netting over the surface of the embankment. The badger sets were infilled using geopolymer with the injection tubes inserted through the mesh, so there's no need to remove the mesh. And the works were undertaken in a blockade due to access issues on that site. So coming up to half an hour now. So this is just the end of my presentation. So the key contacts for rail related works at GeoBear are Steve Farr, our UK rail manager, and Paul Garthwaite, our UK director of commercial and infrastructure. Here's a nice recent picture of the GeoBear team. So thank you very much for listening. Please let me know if you have any queries in the chat there, and I'll endeavour to answer them.
Okay, I know you can't hear me, Sam, but thank you very much for the presentation.
Concrete side bearing foundations, overhead line masts. Sorry, Andy, I see you speaking, but I can't hear you. So, thank you, Adam. Okay, so I think concrete would probably be more ideal in the outset. However, if there was an issue with the performance of those foundations, absolutely, geopolymer can be used for the purpose of ground improvement to bring that movement to a halt. And the expansive properties of geopolymer would certainly help with any issues you're having with overhead lines. We'd need to, with project specifics and awareness of ground conditions, awareness of the moments that the foundations put under, we'd look at how we could resolve any issues with overhead lines. Andy, yes, we've actually recently presented. I think my colleague has recently presented on a transition zone. It's a project in Ireland where we injected progressively from a lightweight treatment to a much heavier treatment, and to improve the transition zone and to improve the ride from that bridge, which was the hard point, to the embankment which had settled. We have a patent for that methodology. So absolutely, if there's issues with soft spots to hard interfaces, whether that be a tunnel, whether it be a bridge, then certainly we can assist with that. I'm happy to share the slides. So that's no worries at all. So, yeah, thank you for your question, Jeremy. So, the material geopolymer can be injected into loose soils, and it will migrate through the void space, and it will bind the materials. Again, if we are able to look at specifics, I'm more than happy for you to email me or share details of with my colleagues or myself, and we can look into the specifics for you. But certainly it can be used for the purpose of binding. We've used geopolymer for ballast binding. It certainly has the capability of doing that. Pradesh, can we use it with reinforcements like the way we use concrete to increase the tensile strength? So with the geopolymer, the way it's injected, because it's injected on discrete spacings, we don't tend to rely on any tensile capacity, because we can't always guarantee that the geopolymer itself will create a complete closed system. So typically we focus on the compressive capabilities of the geopolymer. Hope that answers that question. Thank you, Robin. So we use geopolymer for underwater retention structures as a permanent solution. So that the geopolymer's design life is the same as out of water. It's very it doesn't break down. However, we couldn't necessarily inject geopolymer directly into water, a large volume of water, because it's not compressed. Water can't compress unless we can displace it. We certainly use geopolymer to displace water out of small to medium-sized voids. However, in a very large body of water being incompressible, it would not expand or form a decent. It wouldn't fill a void, for example, and it's very lightweight, so we need to be cautious of that when working underwater. We use geopolymer to fill the voids, the brick rings in a tunnel. So the case study was for behind brick lining, avoiding behind brick linings. That's typically what we've worked on, to my understanding, although there's lots of experience in the business that I'm not necessarily aware of. What we have to be careful of when we're working with brick structures is that we don't put any excessive stresses on structures that are such as brick tunnels, where they might want to give if we put too much localized area. So often we use kind of weep holes effectively to expansive stresses to escape if they were to become too much. I think I'd need to know a bit more exactly what you're saying there with the brick rings, but I think if you mean inside 2 layers of bricks, that might be it might be a little. We'd need to look at the specifics just to understand if that can be done, but sometimes we have to be a bit cautious with such things. Thank you. Sarah, does geopolymer effectiveness change depending on the type of water ingress? We have I believe we have testing in freshwater and seawater, but I'd need to double check and if you to email me and I'll look into that. If we haven't, then certainly we can do that. But my understanding is we have that data and we could share it with you. Because geopolymer have been utilised for remediation and treatment of mining voids. Yes, so we've used geopolymer for the remediation of voids associated with mining and natural cavities. So there is certainly we have mass void filling geopolymers. There is a kind of size of void that where using geopolymer isn't really viable. It's a very substantial void. It will be it would take longer to do using geopolymer than using alternatives. But we've certainly dealt with solution features, chalk solution features, small kind of mines, like mines that have been backfilled, like Dean holes that have been backfilled with poor soils, or where there's been collapsing and some collapsed soil into a Dean hole and there's voiding. We've filled in voids, but there's essentially a point where the void becomes too big or too deep, where it's not necessarily where geopolymer isn't the right solution, but certainly we have filled voids associated with mining and other and natural voids.
Thank you. Are there any more questions from the audience, please?
Okay, great. Thank you all. Andy, I'm not being able to hear anything, so I guess I'll leave that to you.
Okay, well, my main thing is to say thank you very much to Sam for a very interesting presentation and for handling all the questions in very difficult circumstances. Very much appreciated. The next Lunch and Learn event is on the 10th of June. Multi-source data for proactive railway track maintenance, looking at the A2 corridor in the Netherlands. And then on the 2nd of July, we're running the Electrification and Innovation and Decarbonisation Conference in Cardiff. Details on the website. I think that's fundamentally everything. I'm very grateful to Sam for doing the talk in very difficult circumstances. I hope you've all enjoyed it and look forward to seeing you at a future event. Cheerio, everyone.
Yes.